Okay, now we want to continue on the subtopic of 4.3, the X15 and its wedge tail. So before we had a break just now, we have already gone through the shock expansion theory. So we seen the combination of the shock wave theory as well as the expansion wave theory in the application on supersonic airfoil. There are two cases over there where we have already looked into the flat plate application as well as the diamond wedge airfoil shape. Okay? So now we would like to go into a more realistic example, which is the X15, the experimental aircraft X15 and its wedge tail. So if we look here, this is a top view illustration of a wedge-shaped tail on the experimental aircraft X15. So we are looking at from the top, all right? So if you examine this photograph of the X15, which is known to be the hypersonic research vehicle. So the viewpoint in this photograph is looking down at the top of the vehicle, and we would like to concentrate on the vertical tail at the rear end of the airplane, right? So we want to concentrate on this vertical tail. Vertical tail, you imagine you look from the top, there is a wedge type of structure, which is actually the vertical tail at the rear end of the plane. So this is the front end. So this is the rear end, this is the wing, and this is the horizontal stabilizer, and this is the vertical tail that we are talking about. All right, so I hope you can visualize the situation over there. Right, what we can see here, the cross section of the vertical tail is clearly seen over here. Like a triangle over here. It is actually a wedge cross section, which is in contrast to the type of thin symmetric airfoil sections usually employed for vertical tails on ordinary airplanes. So basically, the wedge shape is further emphasized by examining this particular figure, which shows a drawing of the rear top portion of the X15 aircraft, and the included angle of the wedge cross section is 10 degrees. And there's a given over there. Basically, 10 degrees is from the side to the other side. Okay, so this is what we are talking about, the wedge. So it is a 10 degrees angle. So what we can see, know over here is that the wedge tail is one of the unique design aspects of the X15. Of course, earlier they have different type of vertical tail, so they end up to finalize it with this design, and the wedge tail design, and it came out of concerns in terms of the stability problems at hypersonic speeds. So the earlier X1 and X2 supersonic research vehicles had encountered such problems at much lower Mach number, and one of the major early concerns in the design of the X15 was to find a solution that would provide stability up to Mach 7. So if you had a chance to look into the various earlier design of the experimental aircraft, from X1, X2 up to X15, you can see the what we call it as the changes, the evolution of the design made when by the designer to provide stability to the vehicle. So the answer was provided by C.H. McLellan and NACA engineer at the NACA Langley Memorial Laboratory. And McLellan had carried out theoretical calculations of the influence of airfoil shape on normal force at hypersonic speed. So he found out that a wedge of 10 degrees was more effective than a thin supersonic section. Imagine the earlier design is just a vertical thin shape, right? But it is not providing enough stability at a higher Mach number. So from the experimental that being conducted by the NACA engineer, so they found out that a wedge of 10 degrees provided an effective stability. All right. So the X-15 designers were aware of McClellan's work and designed the aircraft with the 10 degrees wedge tail that provided adequate directional stability for the hypersonic vehicle. So that's the story behind it. Of course, there are a lot of calculation involved. There are a lot of wind tunnels involved, computational fluid dynamics, and actual flight testing. All right. Now we would like to go into an example with regards to this situation. So we want to see whether the explanation given earlier makes sense or not by looking at this example. So there are two cases over here, where we can see here a schematic of hypersonic flow over a flat plate. So the top portion of this figure A, is a flat plate, and the bottom part of the figure is the wedge, the triangular wedge over there, both at 10 degrees angle of attack. So similarly here, the alpha angle of attack is given as 10 degrees, same for the wedge case and the flat plate case, right? Both at an angle of 10 degree in a Mach 7 airstream. So it is at hypersonic speed, Mach 7. So both the flat plate and the wedge are experiencing a Mach number of 7. You want to calculate the lift coefficient, the CL, on the flat plate, and at the same time, we also would like to calculate the lift coefficient generated on the wedge. All right. So let us go through one by one in terms of trying to get the corresponding values for the CL and for the both cases. Okay, let us consider the first part of the question, the flat plate case. First, consider the expansion wave. So from our theoretical understanding earlier, for a flat plate case, the flow on top of the top surface will experience expansion wave. So you can see here expansion wave, whereas the flow going through the bottom surface is experience an oblique shock wave. And we know P2, okay, the pressure uniformly distributed on top of the surface is less than 7, which is P1. At the same time, the pressure distribution on the bottom surface, P3, is greater than Mach 7. Okay, greater than the pressure at pressure of P1. Okay, so and then we know also the P3 is more than P2. Okay. And from Appendix C, so if you look at Appendix C, the Prandtl-Meyer table, okay, we look at Mach equal to 7, you will read that V1 equal to 90.97 degrees. And from the earlier equation, V2 equal to V1 plus alpha, where alpha equal to 10 degree, you will then obtain the value of V2 as 100.97 degrees. So what you need to do is basically interpolating to obtain M2, right? Similarly, from the example 4.1 earlier, we also interpolate to get the value of M2 from Appendix C. So you use the same formula in terms of interpolation, where you get the value of M2 to become 9.56. So you now already know M2 is 9.56. Okay. Going into isentropic flow table in Appendix A now, and interpolating for the pressure ratio P naught over P. Between entries, we have P naught 2 over P2, which is equal to 0.33 times 10 to the power of 5. Right? And also from Appendix A for Mach number of 7, we have P01 over P1 equal to 0.14 times 10 to the power of 4, right? So since we know P0 is constant across the expansion wave on top of the surface, okay, so we use this expression where pressure ratio P2 over P1, we put down the values that we obtained earlier, okay, P01 over P1 on top of here, and P02 over P1 that we have already obtained from our previous slide just now, 0.33 times 10 to the power of 5, and you will get the pressure ratio P2 over P1 to become 0.1255. All right. So what to do next? Now you need to consider the shock under the bottom of the of the plate. Just now is on the top surface. So using the diagram of theta, beta, and Mach number. So you use the same technique. So at Mach number of 7. So basically in the chart you see there's Mach number 6, 8, 10, 20 and infinity, right? So basically Mach number 7 is in between 6 and 8, right? So it is quite small over there, but if you manage to zoom in, zoom in, so you can there's an imaginary line of Mach number 7. So we trace it to coincide with theta equal to 10 degree, right? That's why the angle of intersection over there, right, it is in between Mach 6 and Mach 8. So just in between there, and you will get a value of 16.5 of beta. All right. Again, I just want to remind you, this is 16.5, maybe quite very accurate. You may resulted to get a value of 18 or 16, right? So to get it as accurate 16.5, you may need to enlarge it a little bit further. So from here, you can then use the expression for M and 1. You know already beta. Put the value of beta over there, and the Mach number 7 sine 16.5 degrees, you will get 1.99 to become MN1. So then you use the Appendix B, because this is an oblique shock case condition. So use Appendix B for MN1 equal to 1.99. You will then need to interpolate to get the value of the pressure ratio P3 over P1, where you can then put down the numbers. You will get, this is a number from the table. You get P3 over P1 to become 4.45. I hope you can follow the steps here. And what happened? To obtain the coefficient of lift, and the lift coefficient for a supersonic or hypersonic flat plate was derived in example 4.1. So we had this expression before. We just need to put inside the number. We know already P3 over P1. We know already P2 over P1, and the corresponding value of gamma and Mach number. At the same time, you have a alpha, the angle of attack of 10 degree. Then you will get the coefficient of lift for the flat plate at Mach 7 to become 0.126, right? So this is the value for the coefficient of lift for the flat plate, right? Now we want to continue for the wedge, shape. All right, so this is the wedge shape. This is the for figure B, right? So using the same expression, V2 equal to V1 plus 5 degrees, you will then get, why 5 degrees is because of the wedge itself is 10 degrees, right? But 5 degrees on top, 5 degrees on the bottom. So that's why V2 equal to V1 plus 5 degrees, which equal to 90.97 plus 5. So you get 95.97 using Appendix C. Okay, Appendix C, Prandtl manner, because the wedge will create expansion. So expansion on top and oblique shock on the bottom because it has angle of attack of 10. If it does not come with angle of attack of 10, it will only it is similar at like the diamond shape, diamond wedge, but not in this particular case where we need to interpolate for the value of M2, right? So you will then get M2 to become 8.1 from Appendix C, right? Using the same method just now, using the same method. And then from Appendix A, you then interpolate the pressure ratio P02 over P2. You can then obtain a value of 1.0897 times 10 to the power of 4. All right. Okay, the relationship between the chord length, we have the chord length of the wedge and the length of the face of the wedge. Let me just show you where is the length of the face of the wedge. So basically, this is the length of the face of the wedge from here to here, okay? And then we also have the chord length, the length of the face of the wedge and the chord length of L, okay? Sorry. Right, the chord length of L, right? This is the chord length of L over there, right? So you then can find the L equal to chord length C, divided by cos 5, right? So you can then get the length of the face of the wedge itself, right? So which is equal to C over 0.996, right? So, and which is cos of 5 degrees, right? So you can try to zoom in there and try to find out what is the, so basically you have the dotted line there, and the face of the wedge itself. You want to find what is this dotted line, right? So you use cos 5 degree equal to the you get the value of this dotted line and the L line, L length, right? And then the force per unit span for F prime 2 acting on the top surface of the wedge is can be obtained by this expression, right? So where we know P01 over P1 and P02 over P2 for Mach number of 7 from Appendix A, we have a value of pressure ratio equal to 0.414 times 10 to the power of 4. Thus, you can then put inside the numbers because we know P01 over P1, which is 0.414, and we also know P02 over P2 that we already obtained earlier, which is 1.0897 times 10 to the power of 4, and you will then get the expression of 0.38 times P1 times the wedge length. Wedge length, as we have already obtained here, 1.004 chord length. Okay. Now, using the same theta beta Mach number diagram for the shock under the bottom of the wedge, so we similarly at Mach 7, the theta is now 15 degrees, right? Because what? 5 plus 10. 5, maybe we can just show back. So it is 10 degree plus 5 degrees. So it become 15 degrees. 15 degrees. Right? So 15 degrees of theta. Okay. Which you can now in the same Mach number 7, you trace it back to theta equal to 15, and again at Mach number 7 is just in between 6 and 8. You will then eventually get the beta value of 23.5. From there, you can then obtain MN1. MN1, which is equal to 2.79 by putting the numbers over there, where you can get from Appendix B, interpolating, you will get the pressure ratio P3 over P1 to become 8.915. All right. It's a little bit tricky over here, where you have to ensure the angle now is no longer 5 degrees, it is no longer 10 degrees, it is 15 degrees because of the wedge there, right? So this is considering on the top surface. So the force per unit span F3 acting on the bottom. Now we want to consider the bottom surface. Earlier it is on the top surface, right? So what happened on the bottom surface of the wedge, right? So you get F3 equal to P3 L, the length of the wedge. So you can obtain 8.915 P1 length of the wedge. So the lift per unit span is the combination of the components of the top force and the bottom force, F2 and F3. Let me just show you back. So basically this is F2 that we already calculated earlier, as well as F3. So you want to see whether is it generating lift or it is not. So you can see here, it is a combination of the components which is perpendicular to the free stream. And we examine figure B, we see that the lift is actually equal to the force 3 cos 15 degrees minus force 2 cos 5 degrees. So you can get that value, and rearranging it by knowing the value of F3 and F2, you will eventually get the lift value to become 8.232 P1 length of the wedge, L. However, we know that L equal to 1.004 chord length. So you replace this L to be 1.004 C, thus you will get that 8.265 P1C. So the lift coefficient, you use the lift coefficient equation, then since we know the lift equal to 8.265, so P1C, then you put inside the value over there, and you will solve this equation where you cancel out the P1 and P1 over there. Then you also cancel out the length of the chord of the wedge. Then you will get a value of the coefficient of lift to be 0.241. So you have to ensure that the steps are taken closely, so that you can track back which values to be used, and try to understand the equations, as well as how do we get the final answer over here. CL is 0.241 for the wedge case, compared to the flat plate earlier, we get a lesser value. Right. A little bit of discussion over here. From the results of example 4.2, the lift coefficient of the wedge is basically double that from the flat plate, right? For a vertical tail surface, the lift is the side force. So you want to, basically it is a side force that creates the restoring yaw moment, okay? Because it's a vertical stabilizer, right? Provided by the vertical tail when the airplane experiences a disturbance or displacement in yaw, because the vehicle itself is traveling at a very high Mach number, hypersonic Mach number of 7. So any disturbances, if not corrected, will be a disaster. Clearly, the wedge provides a much stronger restoring moment, so it can stabilize the vehicle itself than a very thin airfoil shape. Because if it is a very thin airfoil shape, the resultant forces, the lift itself is very small compared to the wedge surface, right? As presented in figure A earlier. So physically, the wedge at an angle of attack when compared to a flat plate at the same angle of attack is taking advantage of the non-linear nature of supersonic shockwave. So this is the physical meaning, the physical explanation of the theory and example that we have already seen just now. And when the flat plate in example 4.21 for the flat plate case is pitched to a 10-degree angle of attack, the deflection angle of the flow over the bottom surface is also 10 degrees. All right. So in contrast, for the case number 2, example 4.2, 2 Roman, okay, for the wedge at the deflection angle of the flow over the bottom surface is already at 5 degrees when the wedge is at 0 angle of attack, and then it is increased to 15 when the wedge is pitched to an angle of 10 degrees, right? So 5 plus 10 is resulted to 15 degrees of angle of attack. So this gives a shockwave angle for the wedge of 23.5 degrees, larger than the 16.5 degrees wave angle for the flat plate, right? So examining the equations, I'm very sorry I didn't change this equation. Maybe I will just refer back to the Anderson book, so we can relook back what is equation 913 and 916. Okay, we note that the pressure ratio across an oblique shock varies essentially as the square of the wave angle. Okay, so this is why the pressure ratio on the bottom surface of the wedge, for example, for the wedge example, is twice as large that for the flat plate in example 4.21, and this is 4.21, okay, which resulted to be pressure ratio of P3 over P1 equals to 8.915 for the wedge compared to only 4.45 for the flat plate. All right, so the wedge, by already starting with a flow deflection angle at 0 angle of attack, gets more bang for the buck. So basically it has a more advantage at angle of attack. All right, so that's why the solution of having a wedge compared to the flat plate is much more desirable and already being adopted in the X15 experimental aircraft. All right. Now we want to move into the final subtopic, which is talk on the viscous flow shockwave boundary layer interaction. So this is also an important subtopic to look into the application of shock theory to analyze the supersonic flow over flat plate and airfoil. The shock waves and boundary layers do not mix. So we know already that the development of boundary layers as well as the shock wave, they do not mix together, and bad things can happen when shock wave impinges on a boundary layer. All right. So when you design your nozzle or inlet, okay, so you want to make sure that the shock wave that generated does not mix with the boundary layer. So unfortunately, the shock wave boundary layer interactions frequently occur in practical supersonic flow. So ideally it is not. We want to make sure it is not happening. But for the real case or practical situation, it is happening. And therefore, we want to pay attention to this interaction in this last present section. So the fluid dynamics of a shockwave boundary layer interaction is normally complex, and of course it is extremely interesting to look into the matter, and a detailed presentation is beyond the scope of this book by Anderson. So it is not being covered in detail. However, the author, Professor Anderson, try to provide a brief qualitative discussion that we are going to discuss today. So if we want to consider a supersonic flow over a surface wherein an oblique shock wave impinges on the surface, such as we have seen this earlier in this figure in chapter 3, right? Here the flow is assumed to be inviscid and the incident shock impinges at point B. So basically, a flow started at following at point A is being deflected. Okay, you have an incident shock, and then the flow then directed towards point B over here on the upper wall, giving rise to the reflected shock emanating from the same point. So we have already discussed this earlier, where we can see that incident shock and then reflected shock situation for oblique shock problem. Okay, so there is a discontinuous pressure increase at point B, right? A combination of the pressure increases across the incident and reflected shock. So across incident and reflected shock, we have a pressure increases. Indeed, a point at point B is a singular point where there is an infinite large adverse pressure gradient. Imagine that suddenly we have a boundary layer along the wall in this figure. So you can imagine that suddenly we have a boundary layer development, and how does the shock as well as the characteristic, the properties of the flow being changed. There are changes. So at point B, the boundary layer would experience an infinitely large adverse pressure gradient. So these are the basic elements of the shock wave boundary layer interaction, and the incident shock wave. This particular incident shock wave imposes a strong adverse pressure gradient between region 1 and region 2, and then finally region 3, which in turn separates from the surface, and the resulting flow field in the vicinity of the shock wave impingement becomes one of a mutual interactions between the boundary layer as well as the shock wave. All right, so how to look into this matter, right? So this mutual interaction is sketched qualitatively in this particular figure. So we have a schematic of the shock wave boundary layer interaction. So here, for the ease of presentation, we show a shock wave impinging on a lower wall rather than the upper wall from the previous figure. So we just flip it over. So we have the incident shock wave impinges on the lower wall. All right. So in this figure, we see a boundary layer growing along a flat plate. So imagine there is no incident shock wave, just a flat plate. There's a flow on a flat plate. You can see the development of a boundary layer. So this is in your fluid mechanics. So you can see that there is a boundary layer development on a flat surface, right? So because the external flow is supersonic, so in our case now, it's no longer subsonic, less than 1. The free stream Mach number is more than 1. The boundary layer velocity profile is subsonic near the wall. Okay, boundary layer, it is subsonic flow, and supersonic near the outer edge. So basically near the wall, it is subsonic. Near the outer edge of the boundary layer velocity profile, it is supersonic. So at the downstream location, an incident shock impinges on the boundary layer. You can see here there's an incident shock impinges on the boundary layer at that point. So what happened basically? So the large pressure rise across the shock wave acts as a severe adverse pressure gradient imposed on the boundary layer. So it is try to now being disturbed, thus causing the boundary layer to locally separate from the surface. You can see that. So the boundary layer is now locally separated. Locally separated flow, it is detached from the surface. Where we can see here, delta naught is the separation point. And because of the high pressure behind the shock feeds upstream through the subsonic portion of the boundary layer. As we can already said earlier, near to the wall, it is subsonic. Very at the edge there, it is supersonic, and the separation take place ahead of the theoretical inviscid flow impingement point of the incident shock wave. So even though the impingement happened quite late over there, basically the separation took place. It took place a little bit earlier from the impingement point. So in turn, the separated boundary layer deflects the external supersonic flow into itself, and thus inducing a second shock wave, right? So this is where we can see another induced separation shock wave happening before the incident shock wave itself, and identified here as the induced separation shock wave. So the separated boundary layer subsequently turns back toward the plate and reattaching the surface at some downstream location. So basically, incident shock wave will affected the boundary layer to have a locally separated flow, and then at the separation point there will be an induced separation shock wave occur, right? And eventually downstream here, further downstream of the boundary layer, the flow will be reattached and there will be a reattachment shock wave happening. And so the flow will be rippled out throughout the boundary layer. So the separated boundary layer subsequently turns back toward the plate, reattaching to the surface at downstream location. Here again, the supersonic flow is deflected into itself, causing a third shock wave called the reattachment shock wave. So you can see that incident shock wave happening and then induced separation shock wave happening at the same time. We will see further downstream reattachment shock wave also happen. So that's why I said from the Anderson book, it is quite complicated, and what we are trying to understand here is just the basic principles of the theory behind it. Okay. So between what happened actually between the separation and reattachment shock, between the separation shock and the reattachment shock, where the boundary layer is turning back toward the surface, the supersonic flow is turned away from itself, generating expansion wave. As you can see here, there are expansion wave generated. So that's why it is quite complicated, quite complex. So at the point of reattachment, the boundary layer has become relatively thin, right? So at this particular point, this boundary layer thickness is much lesser than the earlier boundary layer delta naught. And consequently, this become a region of high local aerodynamic heating. So this is where there will be happening high local aerodynamic heating happening. Further away from the plate, the separation and reattachment shocks merge to form the conventional reflected shock wave that is expected from inviscid picture as shown in the previous figure. Okay, the figure that we have top and bottom layer. So the scale and severity of the interaction shown here in this figure depends on whether the boundary layer is laminar or the boundary layer is turbulent. So it depends, because it can happen because it is subsonic layer in the boundary layer, right? So it can be laminar, it can also be turbulent. So since the laminar boundary layers separate more readily than the turbulent boundary layers, the laminar interaction usually take place more readily with more severe attendant consequences than the turbulent interaction. However, the general qualitative aspect of this interaction in this figure are same for both cases. All right. To conclude, let me just try to finish this up. The shock wave and boundary layer interaction has a major effect on the pressure, the shear stress, and the heat transfer distribution along the wall, where we can see the flow separated, and then the position where we have a high aerodynamic heating. Of consequences is the high local heat transfer rate at the reattachment point. This is where aerodynamic heating happen, which at hypersonic speed can peak to an order of magnitude larger than the neighboring location. That can create problems to the surface. All right. So an example of the effect of the wall pressure distribution. So this is the wall pressure distribution is shown below in figure A. So the effect of shock wave boundary layer interaction on A pressure distributions, you can see that the pressure ratio over there, and then the location with respect to the boundary layer thickness delta naught, right? So this is values obtained from experiment, right? Compared to the theoretical calculation, right? Over here, the pressure distribution along the wall in the interaction region is plotted versus distance along the wall X. Okay, X, where X naught is the theoretical point of impingement. X naught is theoretical point of impingement, and X is basically the distance along the wall. Where X is theoretical point of impingement for the incident shock in the inviscid flow case, and the pressure distribution shows a step-like increase with an intermediate plateau. So it is a step-like increase, and then it is plateau at the other part. All right. So this distribution is typical of the shock wave boundary layer interaction. So the external flow is at Mach 3 ahead of the incident shock, and the boundary layer is turbulent. The solid curve is a computational fluid dynamic. This is from simulation, okay, theoretical calculation using CFD, and the circles are experimental data. Notice that the pressure increase extends a distance equal to about 4 times the boundary layer thickness ahead of the theoretical inviscid impingement point. If we look at the shear stress distribution as shown in figure B over here, in the pocket of separated flow, the shear stress tau W becomes small and reverse. You can see that it is becoming small and reverse, and it increases back again. Due to the low energy recirculating flow, and because of the consequent creation of the separated flow, which increase loss of total pressure and high peak heat transfer rates, shockwave boundary layer interactions usually should be avoided, right? As much as possible in the design of supersonic aircraft and flow devices. So you have to, the adverse effect of the shockwave boundary layer interaction as being highlighted earlier. It should be avoided, even though in the practical situation it happened. That's why the aerodynamic designer of aircraft, especially for supersonic and hypersonic vehicle, right? So they must ensure that as much as possible, try to avoid the shock wave boundary layer interactions. All right. However, So this is easier said than done. As I said, it is quite easy to say, oh, it's difficult and so on. Should be avoided, but it is very difficult in practical, whereby shockwave and boundary layer interaction are fact of life in the practical world of supersonic flow, and that is why we have discussed their basic nature in this particular section. On the other hand, modern creative ideas have led to the beneficial use of the separated flow from shockwave boundary layer interaction to enhance the off-design performance of jet engine exhaust nozzle, and for certain type of flow control, so the picture is not entirely black. So basically, there are continuing research going on, especially if you are interested to further your study at the master's or PhD level. So this area, this type of area, hypersonic flow, hypersonic aerodynamics, supersonic aerodynamics are still in investigation, and there are a lot of interesting research can be done in this particular area. So with that, thank you very much for your attention. Maybe there are questions would like to be asked by students or things that can be discussed before we end our session today.